Hello, Jim Winslow here with some more physics. Today I'm going to start talking about gravitational redshift. It's actually going to be the start of a four-part series. The reason there's so many parts is because we have to explain what the current theory is and the physics behind it before we can explain how the new theory works. Let's start with electromagnetic waves. Electromagnetic waves are oscillating electric fields. They are created by oscillating currents. Examples of this are antenna, lasers, heat sources. They travel at the speed of light. They have a frequency which is measured in hertz, cycles per second. For example, 1 megahertz equals 1 million cycles per second. Electromagnetic waves have wavelength. An example would be 800 nanometers would be 800 times 10 to the minus 9 meters. And light speed is equal to the frequency times the wavelength, where lambda is the wavelength and f is the frequency. As f goes up, lambda goes down. Let's go into more detail. At the top we have a relatively low frequency electromagnetic wave, and on the bottom a relatively high frequency electromagnetic wave. The distance between the peaks is the wavelength. If this wave is moving to the right at the speed of light, and you counted the number of peaks that went by in 1 second, that would be the frequency. So here we have the variables that we use. C is the speed of light, lambda is the wavelength, and f is the frequency. Now look at the bottom wave. The wavelength is shorter than the wavelength on the top. If this is going by at the speed of light, the same speed as the top wave, more peaks will go by in a second, so therefore the wave with the shorter wavelength has the higher frequency. As lambda goes up, f goes down. As f goes up, lambda goes down. C is constant according to current theory. Now let's talk about the visible spectrum within the electromagnetic spectrum. Here's a graph of the electromagnetic spectrum. To the right are low frequency electromagnetic waves. On the left are high frequency electromagnetic waves. Examples of relatively low frequency electromagnetic waves are radio waves, AM, shortwave, TV, FM, radar, which is microwaves, and the high frequency electromagnetic waves are X-rays and gamma rays. In the middle we have light rays. Of light rays we also have a visible light. Certain electromagnetic waves are detected by the eye. The lowest frequency electromagnetic waves detected by the eye we see as red. The highest frequency electromagnetic waves we detect with the eye are seen as violet, and the rest of the electromagnetic waves within the spectrum we can see at various different colors. You see blue, green, yellow, red. Now we go above ultraviolet. Above violet, we end up in the range of ultraviolet. Ultra means above. You cannot see these light waves. They give you sunburn. Now at the opposite end of the spectrum, the low frequency end of the visible spectrum, if you go beyond that, you get infrared light. Well, infra means below, so what that means is below red. If the air is cold out and you feel the warmth of the sun are the infrared rays. So let's say you have a green laser beam, which is right in the middle of the visible spectrum, okay? And its frequency turns out to be lower than you expected. Well, what we say is that the laser light has been redshifted. Redshifted means the frequency has been shifted to the lower end of the spectrum. So what is gravitational redshift? Gravitational redshift is simply redshift caused by gravity, which translates to the lowering of light frequency caused by gravity. Let's give you an example. We're going to have a green hyper laser cannon. That means a really big laser. What we're going to do is we are going to bring it to Earth. We're going to have it on Earth to start. And we're going to measure its initial frequency. We're going to call that Fi. Then we are going to move our laser to a faraway large massive object and point that laser back at Earth. Turn it on and then go back to Earth and remeasure the frequency. What we find is we get a frequency lower than Fi. We call that FRS, the redshift frequency. FRS over Fi will be less than 1. What has happened is, as the laser beam has traveled from the large massive object to the Earth, gravity has acted upon it and lowered its frequency. That's what gravitational redshift is. Let's talk a little bit about photon theory. Photons are like little bullets. They travel at the speed of light. Light sources are like machine guns. Photons are the bullets. Light beams, like our hyper green laser cannon, are like stream of bullets. They travel far and straight, bounce off of targets, and impart heat energy to targets. This makes some sense, you know. So let's go into the current theory of photons. So at the top we have a low frequency photon, on the bottom a higher frequency photon. Now photons are little bursts of light. Nobody really knows how big they are or how long they are, but what we say is their energy is proportional to their frequency, where h is Planck's constant, f is the frequency, and E is the energy. So if you measure the frequency of this photon up here and multiply it by h, you get its energy, and you do the same for this one, you get this photon's energy. It turns out because this photon has a higher frequency, it has a larger energy. Stay tuned next time where we talk about a hypervelocity machine gun leading to more photon theory, which eventually leads to current theory on gravitational redshift.